go to webinar screen.
I have it.
It's probably that one right there, right?
Yeah, I have it maximized on my screen now. So,
Right.
it's over to you.
Okay.
Muted.
Thank you, everyone, for attending this presentation of atomic force probe analysis on non-visible defects in sub-100 nanometer CMOS technologies. And oops, there we go. The purpose of this presentation is to illustrate that when no visible defect is found by means of physical analysis, at this point we have to rely on the electrical characterization results produced by atomic force nanoprobe analysis to actually locate and identify the probable defect. What's happened to us is that we reached the point where our ability to characterize failing transistors and identify them as failures has actually outpaced our ability now to do a physical analysis and actually get a visual identification of the defect. And in the past, without a visual identification of the defect, the fabs have been very reluctant to do anything. However, when we've gone to 7/100 nanometer technologies, the problem is that they're having more and more yield problems and such where we just can't visualize the defect, and so they have to rely more on the electrical characterization results, and that's the reason for this presentation. So in this presentation, I'll start with an introduction and then present 3 case studies pertaining to gate oxide, and then the second one on implant, and then the third one on BT shift, and then I'll conclude with a summary. So again, as minimum feature lengths for CMOS technology devices continue to shrink well below below the sub-100 nanometer threshold, physical defects that cause device failures are also decreasing in size. And you can see here in the schematic that quarter micron technology, have gate oxide of 50 angstroms. With the sub-100 nanometer technologies, both the transistors are shrinking in both, in all 3 directions, X, Y, and Z, and gate oxides are down to 10 angstroms, which is just a few layers of atoms, actually. So with such small dimensions, our ability with TEM and SEM and such is getting difficult to actually see what's going on, what's causing the failure. So as far as the traditional failure analysis process flow, what we did in the past was with tests identify the failure mode, and then we localized the failing circuit, typically either by functional microprobing or through other techniques such as light emission or Olbert, say. And then, if possible, we did our DC electrical characterization with microprobes of the transistor nodes if we were able to isolate it to a specific transistor and access those transistor nodes. And then, based on that, we did our physical analysis, and we identified the defect by traditional optical SEM fib and TEM techniques. However, for sub-100 nanometer technologies, process flow has changed now. We still test and localize the failing circuit pretty much the same way, but when it comes to DC electrical characterization, the minimum feature lengths of the transistors are so small we can no longer get probe pads down to where we need to characterize the transistors. So that necessitated something different, and that's when nanoprobing came into existence a few years ago, which allows us to probe transistors at the contact level and identify failing transistors. And then with careful characterization, you can identify probable defect. And at this point, we still submit when we identify a failing transistor, we still submit it for physical analysis and do try to identify the defect with scanning capacitance or TEM site-specific analysis, or if you have it, tomography techniques. But increasingly, no defect is found. And so in that case, with no defect found, instead of going directly to process correction, we have to go back and we have to do either more electrical characterization or just use what we have to tell the fab or the manufacturing people, specifically, what part of the transistor's problem, and kind of direct them in their process experiments so they have an idea of what to go look at. And then they can go to their process correction. Okay. Oops. Okay, I'll move on to our first case study here. Gate oxide failure. In the old days, with the older technologies, when you had a gate oxide failure, it was usually due to a gate oxide rupture. And when that occurred, I'll get my mouse going here, that catastrophic event, the rupturing of the gate oxide, would usually damage the underlying silicon. So when you strip the sample back to substrate, you would typically see a hole in the substrate, as you can see here. And that was the easy way to find gate oxide failures. However, for the newer technologies, there's a little bit different problem. And in this case study, we have partial column failure with a signature bit, and this is 90 nanometers SOI CMOS, and it was a SRAM device that we were having problems with. It was also a test chip, and we had access points to the word line and the bit line where we could microprobe, and we could verify that we had leakage here on the pass gate. And you can see here the difference between the fail and a passing bit cell. However, we did a number of physical analysis. Did a thick TM cross-section that would contain the entire width of the active. To take a look at this, we could see that our gate oxide thickness was normal, and we were looking for gate ruptures. And when you have a gate rupture, typically what you see is a little mushroom where the silicon has been recrystallized underneath, if that was indeed your problem. But we didn't see anything with cross-section TEMs. We did a bunch of backside deprocessing also to look at the gate oxide. And again, looking at these, even with a low KEV, we weren't able to see anything necessarily wrong with the gate oxide. And with such thin gate oxides, it's very hard to image the gate oxides. So we were kind of stuck at that point. And then at that point, we got our AFP, and we're able to do our nanoprobing of the failure. This is a topographical image, and here's the failing bit location, and this is our pass gate that we had identified through microprobing as the problem. And we probed it. And what we found, well, with current contrast imaging, we could see that we had leakage on the contact for the gate. When we did two-probe probing with the AFP, we swept the gate to the source and we found resistive leakage. When we swept the gate to the drain, we found diode leakage. And source to drain, we also found diode leakage. And what that pointed us to was the fact that the short was actually on the source side of the channel. At this location here, it destroys the junction of the source to the active here, and that gives you a short from the gate, which was connected to the word line, directly to the bit line, and that's why we were getting a partial column and bit with the gate oxide leakage was the signature bit. And then we saw on the previous page, when we swept gate to drain, you saw the diode. That was this junction here. And then sweeping source to drain also. Again, because this junction no longer exists, when you sweep it, you see this diode also. And with AFP analysis, the nice thing about it is that you can tell exactly where your gate oxide failure is. We looked at some single bits where this gate oxide failure was actually on the drain side, and the curves that you get would be exactly opposite what you see here. It would be gate to drain that you'd have the resistive leakage, and then you get the diode leakages then. And then there were additional bits that had the gate oxide failure in the middle of the channel, and you would see when you swept the gate to the source and the source to the drain, you would see the diode sweeps for both of these. And so you could tell exactly where your gate oxide failure was occurring, whether on the source side or the drain side or the middle of the channel. So based on these results, our manufacturing people went back and did some process experiments, and they actually they changed the pre-gate oxide clean on for this this process, and it basically got rid of all our gate oxide failures for the most part. So based on just the electrical characterization data, we were able to identify that it was indeed a gate oxide failure and not some other type of failure. Say if you had a poly defect that was shorting out on the outside, you wouldn't get the same type of electrical signature that you do for a gate oxide failure. So that was really nice. And in fact, for the most part, when we identify gate oxide failures, typically our manufacturing people accept our electrical characterization results now based on these past experiences. We still attempt a physical analysis to try to identify it. In some cases we can, but more often than not for sub-100 nanometer technologies, we never see anything with gate oxide failures. So this next case study was an implant issue. It was a 90 nanometer CMOS device failure, and the primary cause was a spacer bridging which blocked the source drain implant in the silicide formation, and you can see that here. They didn't have any. In this circuit here, we got a double-gated transistor, and it was the N3 and the N4. And based on their test results, they didn't have any problem finding the failure. They quickly identified with fib cross sections that this was the problem. However, they actually had an argument about whether or not the LDD implant was missing. Some of the people suggested that with an LDD implant, there should be enough conduction between the two transistors for the circuit to operate and not fail, and others didn't think so. So they actually sent me a sample to actually settle the argument. So we took one of the samples and submitted it for scanning capacitance, and here you can see the N3 and the N4 transistors here. And if you look in this scanning capacitance image, you can see that between the two transistors, where it's supposed to be blocked, the source and drain, you can see some implant that's fairly consistent with what's not blocked on the outside, which was an interesting result. That wasn't expected. And so, looking at it on our atomic force probe system, this is the N3 transistor. Here, looking at it at 1.8 volts, we only got about 1 microamp of current here on a correlation unit. Well, this was a passing N4, I guess. We had 52 microamps of current, so you can see a considerable difference here between the two. And so we were able to verify that even though there was some type of implant there, it wasn't sufficient to allow a good conduction between the two transistors. And so that pretty much settled the argument in the fab. So I asked them about what they thought was the reason for seeing the implant in the scanning capacitance image, and the best explanation that they could come up was that even though that they had this bridge spacer here when they did the source drain implant, what happened was that enough penetrated where you got an implant at the surface of the silicon or the active, but it wasn't sufficient enough to actually allow good conduction through the between the two transistors. And that was the best explanation that they could come up with. We didn't do any cross-section SEM on this, unfortunately, but this was good enough at the time for them to actually fix what their real problem was, which was the spacer bridging, and correct the problem. So the next case study we'll look at is VT issues. Voltage threshold problems for transistors have always been difficult to identify. Access to all the transistor nodes is needed to identify a VT delta. Before nanoprobing was available, in my experience, probably 10 years of doing failure analysis, I'd probably only seen I was only able to identify probably one or two VT failures with traditional microprobing. And once we began nanoprobing, we were able to start finding a lot of VT issues, and that was VT issues for in the past would have been no defect found failures, which probably ran at about a 10% level. But with nanoprobing, we could more closely analyze those type of failures, and we find a lot more issues now. And we've been able to reduce our no defect found problem significantly. But VT is dependent on gate oxide thickness, gate oxide trap charge, and device doping. That's traditional VT. Gate oxide thicknesses can be measured with the TEM analysis, but trap charge and substrate doping issues are very difficult to identify through physical analysis. Here in this case study, we had a 65 nanometer CMOS test vehicle that had yield fallout due to single bit failures. At the fab cross-section and SEM inspection at the fab revealed no defect. So I was sent multiple samples to look at. Here you can see in the bit mapping on this sample there were 3 individual single bit cell failures. Looking at the first one, actually saw a significant delta between a passing passing P-channel transistor and a failing P-channel transistor. Nominal voltage typically is 1 volt for this technology, and I had to increase the voltage up to 1.8 volts to actually see where the VT occurred. Even so, with that, well, the issue was there a source drain issue with the contacts, where were the implants missing on the source drain? So I went ahead and did 2-probe probing, source to well diode, looked at that, and it looked relatively normal, failing versus passing, and then drain to well diode also, and then gate to well leakage. So with those results, we were fairly confident that the issue wasn't due to a resistive contact or a missing source drain implant. It had to be due to something else. We did cross-section TEM analysis of the failing P-channel transistor, and it showed no anomaly. Again, no missing silicide or anything like that, or some other type of defect that we could see. Submitted the sample for scanning capacitance scan. Again, the results were inconclusive, and here you can see this was the failing P-channel of interest, and over here you can see the scanning capacitance results for the failure compared to passing P-channel transistors, and there's no difference that can be detected as far as the doping of the source strains in the channel. So the problem with scanning capacitance, however, is that it's more of a qualitative tool rather than a quantitative tool. I did actually the calculations for that, and I found that you can have a 50% change in device doping, and it'll produce a 200 millivolt change in VT, and that's often enough. That's often enough to cause a bit cell failure. However, 50% change in device doping you won't see with scanning capacitance. So again, our physical analysis tools kind of let us down now. So these results were reported to wafer manufacturing, and based on the electrical characterization results, they had to perform process experiments to identify and correct the problem. And we were never able to actually visualize a defect with our physical analysis tools. Oops. So in this presentation, challenges of performing failure analysis on sub-100 nanometer transistor technologies are significant. The number of failures where no visible defect is found by physical analysis is increasing. Electrical characterization by means of AFP analysis is being relied upon to identify probable defects. Then the wafer manufacturing facility is having to make adjustments to their process based on electrical analysis results rather than physical analysis results. And in the future, continued improvements in techniques for AFM, nanoprobing, high-resolution TEM, and other types of new physical analysis technologies will be needed if we're going to actually catch up with our electrical characterization ability and actually visualize defects again. That concludes this presentation.
Unmuted.
Oh, thanks, Randy. That was, as always, with your presentations, very interesting. I've had a couple of questions come through whilst you were presenting. The first one, and unless anybody would like, I usually keep the questions anonymous or first names. So I've got a question from a user, Chang, and he'd like to know. His question really is for case 2, and with case 2, he'd like to ask the question as to whether or not TEM is enough to find the problem alone without nanoprobing.
On case study 2?
Yes.
Okay. Actually, with the newer models of the TEM, we recently upgraded to the recent Joel model. And our TM expert has been experimenting, or he's been developing holography technique, which allows the TM to look at source drain implant. And with that capability, you can relatively easily see the source drain implants. However, for holography to work, it has to be heavily doped. So typically you see the source drain implant diffusions, but the lightly doped drains, as well as the lightly doped, well, if you have bulk, doesn't show up very well, and so you're kind of limited by that. But as far as the source drain implants, they're very visible, and with that technique for case study 2. We could have probably have seen more of the implant, but we didn't have it available at the time we were looking at that failure, unfortunately. But this is what I'm talking about. As the improvements of our physical analysis techniques catch up to our characterization techniques, we should start seeing more and more of these type of failures, or what's causing these type of failures.
Oh, thanks, Randy. I have a question from Adam, and he wants to ask: is the AFP capable of performing functional probing on packaged parts, or do you still need to use traditional microprobing with pico probes?
That's a good question. I haven't tried a packaged part yet.
Yeah,
Not familiarity
yeah. I guess
with the
it's
tool.
it's a question that that maybe from a multi-probe perspective we can help answer. The
Hmm.
the ability to probe packaged parts is somewhat difficult because of access to the material around the with it in the package. So currently on our systems, it's difficult to probe a packaged part, but it's not impossible. Typically, users would would depackage the device. I think Randy would confirm that. Typically, it would be a
Hmm.
depackaged device down at metal or contact, and then probe directly.
Yes, that's correct for the most part. Thinking about it, you could possibly use the fib to open up if say you were interested in probing on metallization line. Um, you could, and you wanted to leave, especially if it was the top layer of your metallization. If you wanted to look at it for some reason, you could open a window with your fib and access the middle lines. And then if it's just the package part, depending on how thick the package is, um, I could see it. I could see it fitting in there and being able to get the AFP tips down on that to do measurements. But it would be pretty limited to pretty much that kind of measurement.
Okay, there's a question from Mark. Mark would like to know whether or not you do all of your probing at contact, or if you ever probe at metal 1, and if so, do you have any problems maintaining picocurrent contrast and electrical connection with the sample and the probe?
Um, we actually do quite a bit of probing at metallization now. It's just it's becoming required as the number for 700 nanometer technologies, as the metallization layers continue to increase. Our analysts, their ability to do microprobing to isolate it to a specific circuit and then hopefully down to a specific, one or two transistors, is becoming more and more difficult. It's gotten to the point where they can localize through microprobing a number of circuits, maybe some a number of muxes, but they only get it down to that point where they can see the signal going in and coming out, and then there may be maybe a dozen, 2 dozen transistors. That may be the problem. And through partial delayering of the sample and accessing the metal lines at higher levels, we can toggle the input and then see what happens on the output. Or you can look at if you got multiple inputs at a higher layer of metallization, you can probe at that metallization and sweep it and see if any of the inputs going into that circuit is leaky, or on the outputs if any of the drains that are connected together, if you have a problem with those. And you can kind of narrow it down, but it starts to become more laborious because you kind of got to start at a higher level and then work your way down, measuring at different metallization layers. And probably about half of our submissions now we have to probe at metallization, on the copper metallization. And at first we had difficulty with it. It's not easy when you first do it, but through practice and through some techniques that we use now, we've gotten a lot better at it. We try actually to probe on the metal lines rather than the vias. The vias tend to, when you delineate them so they stick up above the oxide, they tend to deform when you push on them with the probe tips. If you deprocess to the metallization layer, they're supported on the side with the oxide on each side, so they can take much more of a beating and hold up. So we found that works better. The other thing that we found that seems to help is that when we polish down, and say if you want to polish it or probe it via, and you remove that overlying metal layer and you expose the via, you need to delineate that via. We found that it works better actually to use the RIE to remove a little bit of the oxide. It tends to also clean up the top of the copper also, and it makes it easier for your probe tits to establish electrical conductivity to the metallization.
Okay. I have another question from Jay. We seem to have plenty of time, but there's a question from Jay who talks about case study number 1, and he'd like to know, how did you determine the short was through the gate versus an external short, such as a silicide short from gate to source or drain?
Okay. Let me see if I can get back there. That wasn't supposed to. Okay.
Well, have we lost Randy? Oh, we may have lost Randy. He's gone very quiet and he's not responding. Let me check, see if he's still logged in.
With the gate oxide failure, you see this diode here, as well as when you sweep the source to the drain, you also see the diode, and so it's the difference in your electrical signatures that you get. You just see the resistor short here. You don't see these diodes when you have a resistor short when it's outside, not through the gate oxide, and that's the difference.
Okay. I've got one more question. I don't know how long you want to take questions for, Randy, but I've got a question from Igal, and he'd like to know whether you've had any success probing metal lines that are aluminium or aluminum, as you Americans say.
Yeah, we probe on aluminum metallization also. That's correct, and that's typically on the older technologies. But we haven't had to do that much of it. With aluminum metallization, you typically also have the tungsten vias, and so in that case, we're on copper. We wanted to probe on the metal lines. On the older aluminum metallization technologies, we want to probe on the via plugs because they are tungsten and easier to probe. But yeah, we have probed on aluminum metallization, and it works. You got to use your needles. You got to really drive it in and really push on it to establish your electrical conductivity. But it does work.
Okay. Well, I think we seem to have run out of questions, which I don't know if that's a good thing or a bad thing, but I think you've successfully answered all of your questions, Randy, and yet another successful meeting. So firstly, I'd just like to thank Randy on everybody's behalf for an interesting presentation. And then I've been asked by our marketing department if people would fill in the survey that comes at the end to enable us to see if we can improve the venue and see if we can get some ideas for webinars that people would also be interested in hearing and even in presenting themselves. So with that, I think I'd like to thank Randy again. and
Well,
formally
thank you.
close our meeting. Thank you, Randy.
Thank you.